I was saying, we think we're making a step change in post-combustion capture technology, but we can't do that alone. We need collaboration. We need for our technology to be integrated with existing technologies, and that's why partnerships and agreements with companies like Siemens are going to be really important. I'm Trent Harkin, Technology Manager for KC8 Capture Technologies. I'm a process engineer, started in the oil and gas, petrochemical side of the industry, and moved into carbon capture and storage in about 2008. So I've been working on the development of this technology since its inception around about 2010. We're an Australian company, if you hadn't already sort of told from our accent, but we're building in the US. We've just put in our second US employee at the start of this year. So we're building a scalable, low-cost and sustainable carbon capture solution that provides a pathway to reduce greenhouse gas emissions from the use of fossil fuel and heavy industries around the world. We'll be commercially ready by 2025. We've got 2 demonstration projects that will be operational by then. We think we're cost-effective and retrofittable compared to the alternatives out there. And most importantly for me, I think we're sustainable. Our solvent is safe compared to existing post-combustion solvents. We're not a typical amine. In fact, I was doing some cooking last year, which is out of the ordinary. We ran out of sodium bicarbonate in our kitchen, so I went out into the shed where I do some mixing of different chemicals and used our solvent to put in the recipe. So that's how safe it is. I wouldn't do that with any other solvent that's on the market. So that's how safe that our solvent is, and I think that's a really important selling point. So in terms of what our technology is, it's based around a solvent capture technology, but there's more than that in our IP. We're looking at, when you get to utility scale, these are really large scale. So we've got IP in large scale concrete contactors. We've got solid solar absorbers, which become really important. And we look at chemical production, creating valuable products out of there as well to increase the business cases. And we've got a lot of IP in process and heat integration. How do we get these kind of technologies put on the back of power stations or in different industries? At the core of our technology is what's called the UNO Mark III solvent technology. It's potassium carbonate based solvent.
It'll change what
it's a precipitating system. So that's unlike what typical potassium carbonate systems are. They're liquid and actually designed to operate so that you don't get precipitation, because precipitation can lead to blocking of absorbers and things like that. We actually do the opposite. We increase the solvent concentration. So when you carbonate, reacts with CO2, it forms something called a potassium bicarbonate. As you increase that concentration, you form a solid, and the solid drops out. What that actually means is that you can absorb more CO2 into that liquid. And because you have higher concentrations, you're able to capture more CO2 per volume of liquid. And so you decrease the size of all your equipment. So what that leads to, allowing that precipitation to occur and that high use of higher concentration, is a lower regeneration compared to typical amines, a lower overall cost because you've got less solvent firing around, so much reduced equipment sizes. And the fact that it's an inorganic solvent, as I said, I'm happy to add it to my recipes. It's low volatility, very environmentally friendly. So the technology works as most post-combustion capture technology kind of works, in terms of you might have some pre-treatment from the flue gas. It goes through an absorber. So in the absorber, you put in lean solvent at the top, you get out rich solvent at the bottom. And then you go through a stripping column where you heat up the solvent, it regenerates CO2, releases pure CO2. So the difference in our technology is what really happens in the absorber. So it comes in the top as liquid. As it draws down the CO2, it becomes the bicarbonate. As you cool that, so there's some recirculation loops in there to cool down the solvent, it drops out bicarbonate solids, and then that helps to absorb more CO2. So what you get out the bottom is a really concentrated, really highly loaded solvent with solids in it. So this is just another picture of sort of some examples of the lean solvent on the right and some rich solvent with solids settled at the bottom on the left. So the storage capacity of our solvent is about 2 times more than what you'd get in a typical, base amine. But not only that, the solvent cost is a lot cheaper. So that leads to a much more than a 2 times reduction in the solvent costs for the whole plant. So it's important for reducing all those OPEX and CAPEX cost downs. As we get to utility scale, these things are big. Like, so on the back of a 2x1 F-class turbine, 800 megawatts, we're talking about a 20-metre diameter. That's a big absorber. So to reduce costs, you've got to start moving away from traditional post-combustion capture vessels that are stainless steel and all that kind of stuff into concrete column construction. This is low pressure, so you can do that. Not only that, we've come up with concentric column designs. So when you've got a 5-metre stripper and a 20-metre absorber, you can actually put the stripper inside the absorber and build the absorber as an annulus around the stripper, and that reduces the whole footprint. So you go from sort of a 20-metre absorber out to about a 22-metre absorber, but you've got the stripper sitting inside that as well. So that's any plants that are really, if we're retrofitting plants, there are a lot of them are plot plan constrained, so this helps to reduce the footprint. So what does it look like when you add this to a natural gas combined cycle? Well, here it is you've got your normal NGCC, you'll have a diverter from the stack to run it through a pre-treatment system and then into the absorber and stripper combination. The pure CO2 then goes off into the CO2 compressors, into the various pipelines. I want to introduce you to sort of another good benefit of our system, and that's it's called solvent storage. So you can actually time shift regeneration in there, and we can do that economically because of how much CO2 we absorb per volume of solvent. So you can actually, when you add, I think Rick sort of mentioned this, when you add a PCC plant onto an NGCC plant, you reduce the efficiency of the plant. So an 800 megawatt plant becomes something around about a 720 megawatt output plant. So it's about a 10% drop with our system. But what you can do with this system is you can absorb the CO2 at times when electricity price is high but not regenerate. And then you get what was a 720 megawatt plant can probably output almost back up to that 800 megawatts. So when electricity prices are high, you're getting the maximum amount that you can, and then when electricity prices drop, that's when you regenerate more. So we found that that's really valuable in grid stabilisation. So, in summary, our technology can capture up to 95% of CO2 emissions from various industrial sources. Solvent safe. We should have lower CAPEX, lower OPEX than a number of the competitors. So we're targeting 2 markets at the moment. As I said, we've got 2 demonstration projects. First is the power industry, and this is in collaboration on those NGCCs, and the second is in cement manufacture. So that kind of gives us a good range from the 4% CO2 that you'll get out of a NGCC right up to a 20% CO2 that you'll get out of a cement plant. So I want to talk more about the power at the moment. A lot of this work came out of what's called the Flexible CCS program, funded by the US DOE and ARPA-E. So it basically brought together 2 modelling groups, one from Princeton and NREL, to sort of model future grids, and a whole lot of different technologies that might be able to support NGCCs to run in a high penetration, variable, renewable energy grid. So, when you've got a lot of renewables in the grid and you've got fluctuating supply from those, can you actually make CCS work on the back of NGCCs? So what we found is there's 2 ways that was done. So either we got pricing scenarios generated by those 2 modelling groups, and we were able to model what a single plant looks like. The other way was that we provided them our estimated CAPEX, OPEX, ramp rates, utilisation rates, those kind of things, and they put it into their model and saw what does a future grid look like. And our results were good. So this was work that we did in collaboration with 8 Rivers as well. Basically, out of pretty much all scenarios, any existing gas turbine in the grid was retrofitted to have our CCS on the back of it. More than that, so the way that they set up the model was we're only retrofitting to existing CCS, to existing gas turbines, and the grid was sort of constrained to about 10% gas turbines in that system. So most of the time we were retrofitted to pretty much all of those gas turbines by the end of the period. But what we found was that the fraction that those power plants of profit made out of the rest of the grid, so the grid was an optimisation trying to get the lowest cost down, but the fraction of profits that were made by those that had an Mark III on the back of them was significantly higher. So 10% of the actual capacity, but they actually made up to 20 to 40% of the profits. So we found that when we did our NPV modelling of a specific plant with those power price curves, that this actually surprised me, and even in places where the capacity factors of the plants were only about 30%, still had high positive NPV values. So it's the ability of the plant to be able to generate electricity when the electricity prices are high that actually enables the economics to actually work. The other thing that we found through all that desktop studies was that by adding solvent storage on, you get about an additional 10% of the annual operating cost back from that, so the return on investment of that solvent storage is about 2 to 3 years. So what it does is sort of act like a giant battery, but it's actually about the fraction of the price when you figure out the megawatt hour kind of capex cost of that time shifting that you can do. So all that desktop work led us to be successful in the second phase of the Flex program, which is a demonstration of our technology. So we've got a 10 tonne per day plant that's being built at National Carbon Capture Centre in Birmingham, Alabama. In parallel with that, we're working on what's the next scale up as well. This is 10 tonnes a day. We need to get to thousands of tonnes a day. So we've got parallel plans on what's the next plant once this is demonstrated successful, moving up into hundreds and thousands of tonnes per day. This is just a model picture of our plant that will be installed at NCCC. Basically, detailed design's complete, procurement's complete. I'm going out to the factory later this week to sort of check progress. We're expecting it to be installed at NCCC in middle of March, and so starting commissioning in May. So we'll have test results all out by sort of the end of the year is the hope. Yes, just some pictures of our technology. Because it's got solids throughout the solvent, you have to use sort of some specialised equipment in certain parts of the area, like spiral heat exchangers and the like, to make sure that you can handle those slurries. The other thing that we're doing with this build is we're partnering with Siemens. We've got an Omnivice T3000 DCS in the system, so that we're already looking at, what's our scale-up opportunities. This is what's going to be installed at a power station, so we're looking to already develop that code and everything along that works integrated into those power stations. So that's just a look at what it looks like. Here's our plant positioned next to an equivalent size amine plant that runs at the National Carbon Capture Centre. So I'll just briefly touch on the other project that we're doing in Australia. It's called the PACER project. I'll try and get the acronym right. It's Potassium Absorption for Clinker Emissions Reduction Project. So it's a 10 to 20 tonne a day pilot plant. It's basically the same size absorber as you've got on the Unogas project, but because the CO2 concentration is higher, the back end has to be a bit bigger because you're processing more CO2. It'll be installed at a cement plant in far northern Australia, and it's supported by Low Emissions Technology Australia and Cement Australia, where the plant will be installed there. It's a few months behind the Unogas project, so it's probably going to be installed towards the end of the second quarter this year, maybe into the third quarter, but also operating by the end of the year. So it's got a very similar layout to the Unogas facility, but unlike NGCC, and what we'll find at gas plants is that gas plants have utilities. They have heat, they have power, they have cooling water. Cement plants don't always have that, so we've had to bring in our own utilities into the cement plant to support that project as well. And that's what will have to happen as you scale up as well. You have to think of different opportunities to come through. So this is just what it looks like as it's installed at the plant. So thank you. Yeah, I hope you had got some interest out of that. I know we've sort of come from the very broad and narrowed down into our specific process. But yeah, thank you very much for having me, and thanks for sitting through those technical difficulties at the front, which cut me off. Thank you.
Thank you, Trent. So no questions. Well, okay, all right, I was going to.
So on the ZMS presentation, like you had a couple of assumptions like proximity and pipeline availability. So given your assumption, how dependent is your process to policies for kind of economic positiveness? Like,
two parts to the answer to that. One is in time to market. You know, we're finding in certain, let's say, more litigious states in the U.S., that timing for pipeline can really be an unknown, you know, even if permitting has been proposed. We're primarily focusing on 8 states. And those have some certain legislation that allows for fast tracking of pipelines. And so that's one area that we're working with. What are we working with immediately? I mean, we have roughly 2,500 air-breathing gas turbines, say above 200 megawatts in operation. And so if we're really going to make a difference with respect to decarbonization, I think a key part of that solution is looking at retrofit of existing units. So in areas like the oxy-combustion, we're looking at existing power plants. We just announced now a site in North Dakota, 2 that will be going in Wyoming. And those all have proximity, either located adjoining an existing Class 6 well, or where there's within proximity of, say, 25 miles to an existing pipeline. And we feel we can move very fast working with local authorities for that. In the case of the post-capture technology, working with KC8 and also 8 Rivers, there are 2 new greenfield sites that we're starting, and the same story, where we already have good proximity to an existing offtake pipeline, where we already have a supply of natural gas or the fuel that we'll be using. And then with the current market, we need to also really look at transmission, getting the electrons to grid, as we're seeing some very long lead times with respect to transmission. So we really need to keep our eyes on all of those, getting the project quickly in and monetized. As far as directly on the cost of that, it's roughly $5 million per transmission mile running the wires in for high voltage offtake. Of course, that's a factor. We have somewhat the same cost projections relative to pipelines also. Right. So those are the factors.
We're going to have to come to a close. Really thank you for attending, and we're bringing up the next group.